have derived the dynamic equations of electrical machines, and we have started looking at the application of these equations, and we started looking at the induction machine equations and what would be the kind of results that one can get if we use these equations for simulation of an induction machine. Towards that, in the last lecture we started looking at the simulation results for a free running induction machine, and here we have the data for the machine. It is a 400 volt 4 pole machine with stator resistance, rotor resistance, etc. as indicated, and when we do simulate that for a free acceleration, that means the load torque is 0, the applied load torque is 0, and we run the simulation, we find that the machine accelerates in this manner. What we have is here we have the x axis as time in seconds and the y axis as speed in RPM, and we have seen that the speed rises in this manner with certain overshoots and undershoots, etc., and the speed settles down at approximately 1500, about 1499 RPM, which is near about the synchronous speed because there is no load on the machine. And then we saw that stator transients, you see that initial high inrush current that flows and then settles down, and I think we saw in the last class that the amplitude of the sinusoidal steady state stator current is about 8.8 ampere. This of course one can verify using the equivalent circuit analysis. If you consider that the phase voltage is applied across the equivalent circuit and all the equivalent circuit parameters are given here, so one can do a simple circuit analysis assuming that the speed is going to be 1499 RPM. One can find out by circuit analysis that indeed 8.8 ampere of steady state current flows in the machine. From the equivalent circuit it would not be feasible to get how the speed is going to change, that is, if the speed is going to change, increase in this manner and then oscillate and then settle down, all this information is not available from the equivalent circuit. You can't solve for this situation. What you can get from the equivalent circuit is a performance when the speed has settled down, and you must know what is the speed at which it has settled down. So if you know what the speed is, then using the equivalent circuit one can find out how much steady state current is going to flow in the stator, and indeed how much steady state current is going to flow in the rotor. And in this analysis, since there is no load, the rotor current settles down at approximately 0 ampere. No current is flowing in the rotor because the rotor is running almost at synchronous speed. That can be verified by zooming into the rotor current plot as well. One can see really it settles down at about 0 ampere, that means no rotor current that is flowing. The generated electromagnetic torque, this is torque in Newton meter. Now that shows an initial high peak. So you see that the initial torque generated is very high, that is the time during which acceleration occurs, and then you see that there are oscillations in the generated torque as well, which, as it must be, because it is in this region that the speed exceeds the synchronous speed. So one can go back to the speed plot. So one can see that the speed is beyond the synchronous speed in this region, and you see speed is coming down, and the rate at which speed comes down is the maximum here. So you expect that maximum negative torque is available at this point, which is somewhere after 0.05 seconds, and one can see that indeed is the case. So maximum negative torque is available when the rate of fall of speed is very high, and negative torque is there in the synchronous machine because the speed now has gone beyond the synchronous speed, and therefore since the flux is rotating at synchronous speed, it now tries to retard the rotor, and that is manifesting as a negative torque. And then there are these torque oscillations, and finally the torque settles down to 0 Newton meter. It is 0 Newton meter because again there is no load applied on the machine. Then if we look at the loaded behavior of the machine, what we have done in this case is added a load torque that is 0.002 times speed square. Speed obviously is in radian per second. So if this is the load torque, and remember this load torque is going to oppose the generated electromagnetic torque inside the machine, and the resultant of these two is going to be responsible for the acceleration. And with this then again if we look at the speed transient, so the x axis is again time in seconds and the y axis is speed in RPM. We see now that the speed rises in a manner which is very similar to what we saw in the last case. So here again the speed rises, goes beyond the point where it settles down, and then there is a speed oscillation, and finally the speed settles down, and we see that the speed settles down at 1443 rpm. That is a reasonable slip. Because of that slip, it is now able to support the load torque, which we now have given as 0.002 times omega square. So here there are overshoots and undershoots about 1443 rpm. If we look at the generated electromagnetic torque again shows initial high values, which is when the rotor is accelerating. So large torques for the rotor to accelerate, and then finally the torque settles down at this level, which is a value of 45.76 Newton meter. So one can see that this is the steady state torque that is generated by the machine, and this torque must be equal to the load torque, and therefore the net torque is 0. So the speed is maintained at a fixed value. Now input, you see in the input flow of current drawn into the stator, you see that there are again inrush currents, very high inrush currents. One must remember that the experiment that we are trying to do in this case is what is called as a direct on-line start of the induction machine. That means the machine which is maybe connected to the load is there, and you are simply trying to connect the supply voltage to the machine in one single step. The entire voltage is simply switched on to the machine. In that case what happens? That is what we are trying to see here. So you have initially very high inrush currents that are drawn. Again we see that the inrush current here, it reaches a level of at the steady state 17.8 ampere peak, whereas initial inrush we see it is 150 ampere peak, almost equal to 9 to 10 times the loaded steady state current that is flowing. So as we noted last class, these heavy inrush currents that might flow can cause other detrimental effects on your supply system like voltage drops, and then because of voltage drop some other equipments may trip or lamps may flicker and all kinds of effects like that will happen. So here again there would be a DC inrush initial, so you see that this is 150 ampere, whereas here this peak is only 100 ampere, so it indicates it is not really symmetric, and therefore there is likely to be a DC component which then starts at some value and then decays down to 0 as it reaches steady state. And this behavior, what you get here, this can of course be analyzed by means of the equivalent circuit. Again you must know what is the speed at which it is going to settle down, then once that is known one can find out the steady state performance using your circuit analysis. So this is the stator current, and here one can see the rotor flow of current that reaches 15.6 ampere peak, and one can see in 0 to 1 second there are about 2 cycles of oscillation. So that clearly indicates that we have a very low frequency waveform here, about 2 hertz or so, whereas the supply side on the stator, this is clearly a 50 hertz waveform. So one can see that because of the small slip that is there, the flow, the rotor current has slip frequency. And now one can look at what happens if you transform these variables to some other reference frame. This first plot gives us the stator current waveform. Stator current is what we have seen here, the 50 hertz waveform, whatever is shown here. If you were to transform the stator current, that is 3 phase stator current, into the alpha beta reference axis, 2 phase axis, what we can see here is that the 2 phase waveforms appear like a pair of sine and cosine waves. If you look at it closely, you can see that the waveforms are basically displaced by 90 degrees. One can see that if you take one waveform, let's take this one. So if this is the case, you can see that the blue color waveform looks like this, whereas the green color waveform looks something like this, right. So the phase difference is plus or minus 90 degrees, and these are sine cosine pairs that are available, which is what we expected. If you look back, or if you remember back to the lectures where we discussed the nature of the waveforms due to this 3 phase to 2 phase conversion, we remember that these were of sine cosine pair, and that exists right from the beginning, right. You can see that there are only 2. This red line that you see here, the red line that you see in the middle, that then corresponds to the 0 sequence term. The red line is the 0 sequence, that is I0, and because we are supplying a voltage system that is a 3 phase voltage, balanced 3 phase voltage, 0 sequence response from the machine is again 0 and no 0 sequence current flows. This is again true also because even if you were to supply an unbalanced excitation, as long as the machine is star connected, even if 0 sequence component were to exist in the applied voltage, 0 sequence flow of current cannot be there. Star connected plus isolated neutral. In the case of induction machines, neutral is invariably isolated. So that is your response or the flow of currents drawn in the alpha beta reference frame. If you look at the rotor current in the alpha beta reference frame, please note that what we are looking at is the rotor attached alpha beta 0 reference frame. In that again you see that the stator, the alpha beta currents form a sine cosine pair, but they are of low frequency. This is the same as the frequency of the actual stator currents, which means that if you go from the natural 3-phase reference frame to the 2-phase alpha beta reference frame attached to themselves, rotor attached to rotor, stator attached to stator, frequency does not change, frequency remains the same, but the 3-phase variable get converted to variables get converted to 2-phase variables, and here again you see that the 0 sequence component I0 is 0. This again is a result of balanced system and considering a star connected winding on the rotor. The x axis is of course time in seconds, and the y axis is rotor current in ampere. Now we may do the other thing, we may consider all the machine responses as looked at from the stator referred frame. For the induction machine, then for the rotor variables it would be a pseudo stationary reference frame which is then attached to the stator, and here we see that even though these are rotor currents, this is rotor current in ampere and you have time in seconds. So this is the rotor current referred as seen from the stator alpha beta 0 reference frame, and you can see that this interval is 0.1 second, and in 0.1 second you basically have 1, 2, 3, 4, 5 cycles, which means what you have here is 50 hertz waveform. That is indeed what happens. If you look at the rotor phenomena as seen from the stator, you only see a flux rotating at synchronous speed, and which would lead you to infer that whatever is generating the flux could be something that is stationary but excited at 50 hertz, and that is the physical equivalence of the alpha beta 0 reference frame for the rotor. By the same token, one can also look at stator current in the rotor alpha beta 0 reference frame. That means you are looking at the dynamics of the machine or what is happening inside the machine sitting on the rotor, and when you sit on the rotor, the frequency of the flux, the rotating air gap flux, will now be at slip frequency, and therefore you see that the rotor current, or rather the stator current as seen from the rotor side, is at slip frequency. The amplitude would be determined by the manner in which you convert or transform the stator current to the rotor reference frame, and that is what it is. So here again the x axis is time in seconds and the y axis is then stator current in rotor attached frame. In ampere. So one can by this means transform the machine equations and the responses of the machine to look at the dynamics of the system either from completely the stator side or from the rotor side, whichever is advantageous to the particular problem at hand. One would probably use an appropriate description. Now one can of course go to the synchronous reference frame. The synchronous reference frame is the reference frame that rotates at synchronous speed, and if you rotate at synchronous speed, all the fluxes that you will see around you are stationary with respect to yourself, and therefore you see now that all these excitations are then DC flow of current. You have IQS here and you have IDS here, these are then DC currents, and the 0 sequence is 0 in this case also because the system is a balanced system. So you have again time and current in ampere on the y axis. Now in this case both the currents IDS and IQS have settled down at a negative value. This will depend really upon where your reference frame is with respect to the stator current phasor. So if you now draw the phasor diagram, which we will now see, before that the rotor current is also DC quantities, because whether it is stator or rotor, the moment you are in synchronous reference frame all variables look stationary, and therefore you expect both IDR and IQR also to be DC quantities. The phasor diagram, which is the space phasor diagram, I have drawn it normalized with respect to themselves, the stator current normalized with respect to the magnitude of the stator space phasor, and therefore all of them would have an amplitude of 1 maximum. So here you see that Vs is the stator voltage phasor, Is is the stator current phasor, and this phasor diagram can be obtained from your ID IQ plot. The stator current phasor I in the synchronous reference frame is nothing but ID plus J times IQ, and that is what is shown here. Both are negative, and therefore you get, please note that 0 of the imaginary axis is here, 0 of the real axis is here. So this point indeed is the origin, and with respect to that you can then have the stator voltage phasor and the stator flow of current, the rotor current phasor, and these two are phasors of the stator flux and the rotor flux as determined by the earlier equations, that is the psi dr for example is then Lr into IDR plus Lm into IDS, and similarly you define all of them psi qr, then psi dr plus J times psi qr is then the flux phasor for the rotor, and similarly one can define a flux linkage for the stator as well, and these are the two flux vectors. Now what we have seen is basically the induction machine with a DOL start, that is a direct online start. First we saw free running acceleration, and then we have seen the loaded case with some particular load speed torque characteristic. This is a sinusoidal analysis, that means you are supplying sinusoidal voltage to the machine and you want to see how it behaves. The nice thing about these equations is these equations are not restricted to sinusoidal analysis. We have never ever in the development of equations assumed that V and I are sinusoidal. We have always spoken about instantaneous values of voltage applied, instantaneous flow of currents, and therefore these equations are general and can be applied to non-sinusoidal conditions as well, and therefore one can look at inverter fed operation. Just to briefly recollect what this is, we are looking at an inverter which consists of 6 switches, each switch having its own anti-parallel diode. So you have the diodes here, and this rail then forms the DC bus, and you connect a DC voltage here. These points then act as the output points of the inverter. This is a 3-phase inverter, and this is then given to the induction machine which is connected here. And in this simulation that we are seeing, these inverter devices are switched on in this manner. This device is 1 switched on first, and then 2, then 3, 4, 5 and 6, and then it goes back to 1. So that means one switch is turned on or off every 60 degrees, and each switch having been turned on remains on for 180 degrees, and that is then generally referred to as the square wave mode of operation, which is what we have mentioned here. So this is the inverter fed operation of the induction machine. The machine is connected to the same load that we had seen earlier, that's load torque is defined as 0.002 times omega square, and then here you have time versus speed in RPM, and one can see how the machine accelerates and settles down. So the settling down value is more or less the same as what we have seen with the sinusoidal case. So if it is the same as with the sinusoidal case, what is the difference? So here you see the speed variation. The y axis shows speed in RPM, the x axis shows time in seconds. In the sinusoidal excited case, you found that the speed, the machine accelerates and then settles down, the speed is really flat fixed speed, whereas here you see that the speed is oscillating. So it is not a constant speed, it is an oscillating speed. That means there is a speed ripple. The speed ripple in this case is about 1437.5 or so here, and then goes up to 1440, almost 40.5. So it is about 3 RPM ripple that you have in speed. Now whether this ripple is okay or not will depend upon what application this machine is going to run. Maybe in some applications it is not acceptable to have this kind of ripple, maybe in many applications it may be allowable to have this kind of ripple, but whatever it is, one must know what the machine is going to do to decide whether it is acceptable or not. And if you look at this ripple, you see that this is 0.34 seconds and here you have 0.35 seconds. So in this time then you have 1 cycle, 2 cycles and then 3 cycles of the ripple waveform, 3 cycles in 0.1 seconds, not 1 seconds, which means there are going to be 6 cycles in 0.02 seconds. That means in one cycle of the mains waveform there are 6 cycles of the speed ripple, which means what we have is a 6th harmonic ripple in speed. So why is there a 6th harmonic ripple? One can then look at how the machine is going to behave. In order to determine that, one can see that the input voltage waveform will have a 5th harmonic voltage and a 7th harmonic voltage, and they react with the fundamental to get a 6th harmonic torque. So all that can then be seen. So if there is going to be a ripple in speed, that can only come if there is a ripple in the generated electromagnetic torque as well. So if you look at the torque transient, you see that the waveform broadly looks something similar to what we have in the sinusoidal case, but all along you see that there are oscillations. These small oscillations are there, and indeed in steady state one can see all these ripples that are there. this ripple frequency, if you zoom in and see, will be 6th harmonic frequency, which therefore causes a 6th harmonic ripple in speed. One therefore looks at methods by which the speed ripple can be reduced, torque ripple may be reduced, and so on. There are various then schemes where one can look at these things. Stator current. So if there is going to be a ripple in the generated electromagnetic torque, we have seen that the expression for the generated TE depends upon is going to be something like IQS into IDR minus IDS into IQR. So IQS and IDS must in turn have some ripples, which means that the actual input current drawn should also have some ripple or harmonics. So here we see that the input current drawn is not really a sinusoidal current, but has lot of harmonics that are there. Here again there is an inrush current, definitely inrush current will always be there because you are supplying full voltage in one stretch to the induction machine. So it will draw an inrush current to support the huge torque. And here we see a zoomed waveform of the stator current. So this is current in ampere and time in seconds. So here we see that this waveform is clearly non-sinusoidal, is rich in harmonics. What happens because of these harmonics? Invariably they cause lot of heating and I squared R losses, ion losses, eddy current losses in the machine, and therefore may be detrimental, and these harmonics also result in harmonics or oscillations in the generated torque TE and therefore in the speed waveform as well. But if you are going to supply an induction machine through an inverter and not specially controlled inverter in any particular way, simple square wave operation, you just can't avoid giving significant harmonics at low frequencies, and that therefore results in this kind of distorted stator current waveform. Again, after studying all these things by means of all these simulations, one will then need to answer this, that for a given application whether this kind of harmonics are acceptable or not. If they are not, one has to go around finding ways to minimize this harmonic and make the current more sinusoidal. One can see the flow of current in the rotor. So this is rotor current in ampere, time in seconds. Even though you still have the same low frequency, which obviously you must have because the speed settles down at speed with a small slip 1440 rpm. So you expect that the frequency will still be low, and frequency is indeed low, but it again has oscillations which are at high frequency and thereby contributing to ripples in the generated TE waveform and the speed waveform. So this in short is an example of what kind of results one can get by using the equations that we have developed so far for the induction machine, and what kind of studies it can be put to use. You can use it to determine the transient behavior of either sinusoidally excited systems or non-sinusoidally excited systems, but as far as the machine is concerned, what we have modeled is a balanced 3-phase machine. The voltages that are applied may be balanced or unbalanced in whatever manner we want. So one can then use this to study other aspects of machine behavior as well. For example, one can say that you have an induction machine being connected to some load, and maybe it is a direct mains connected machine. It has been supplied with AC voltage from some substation, let us say, and all of a sudden let us say that there is a fault on the lines and all the 3 lines short to ground, what will happen to the fault current that is going to flow in this? On this side there is a source, 3-phase source, and that will send some current into the fault. The induction machine, one may say that there is no source of excitation, it is not a alternator, therefore maybe it will not, but then there is a magnetic field inside the machine which is rotating at synchronous speed, and magnetic field represents stored energy. So if there is a fault, what you would find is that the induction machine also will contribute to the fault current, though it is likely to be a short duration event. It may be worthwhile to study what kind of fault performance this kind of a system gives. So if you want to study that, you need these kind of dynamic equations to see what is going to happen. But then that is not all. If you have a system like this, because of the fault, what is likely to happen is that at this point you might have a circuit breaker. So if you have a breaker here which is there in the line, as soon as fault current is detected, the breaker may open, and if the breaker opens, still fault current, if there is no breaker on the machine side, fault current will still be supplied by the machine. But then what would happen is the breaker may reclose, and then you are now having a fairly severe situation. You are trying to close this breaker when the machine is rotating and there is flux inside the machine. Now this kind of a situation can cause a more severe inrush current than what was happening at direct online start, because it may so happen at the time at which you decide to close the breaker, the supply voltage and the induced voltages inside the machine, because of the flux being there, they might add up and cause a larger current that flows into the machine. So these kind of studies will have to be done a priori in order to determine what kind of behavior to expect from a given system, so that you can probably decide to choose an appropriate breaker or fuse ratings and so on. So this is another aspect of the machine dynamic equations that we have studied. Of course, as we have seen in the earlier, when we developed the the induction machine model in the synchronous reference frame, one can take that along further and then see how the machine has to be controlled. So if you are going to have an inverter fed induction machine and you are interested in closed loop control, you might want to look at strategies like field oriented control or vector control or maybe direct torque control or some other control strategy that you might invent yourself. You need to understand and manipulate these machine equations. So machine control is another big area where these machine equations are employed to a large extent. So let's stop the induction machine discussion at this point. We have seen applications of machine equations from this side, and the next thing to look at will be the alternator equations. Now the alternator equations also we had developed, and let us now look at applications of the dynamic equations of the alternator that we have studied. So alternator dynamic study. We had already looked at the steady state analysis of the alternator, and then we have seen how the steady state equations could result in the phasor diagram, and using the phasor diagram one can then do all your steady state circuit analysis, system analysis where the alternator is connected to the grid and so on. So when we talk about dynamic study of the alternator, it is very important to consider dampers. especially in the case of grid connected operation. Most of the alternators are operated in the grid connected manner. They are the ones that are supplying all the electricity that are of use to you, except that nowadays you have solar power and wind power where the generation is not through the alternator, but most of the power in the world comes from alternators. So they are connected to the grid, and what one may need to look at is at the time of synchronizing the alternator to the grid, what happens to the machine. Normally if you synchronize it in a as it is expected to be done manner, then you will not have much stator currents flowing during synchronization, but sometimes what happens is the synchronization due to some error or the other happens in the wrong way. Maybe the phases are interchanged, or the phase sequence is not right, or the phase they are not at the same phase at the time of synchronization, then huge currents can flow and it can result in severe alternator damage. So how does the current flow, what kind of currents and what kind of shaft torques may result, one will need to make use of the equations that we have seen. Now in all these cases then you will have the rotor rotating at speeds that due to the excess torque that is generated, or the fluctuation in the fields that are there. It would be very much essential to look at how the dampers are going to behave. So let us then put down the equations of the synchronous machine with respect to dampers, with respect to these kind of analysis. There is another important aspect of alternator study, because they are generally grid connected. One of the important aspects of alternator performance is if you take the alternator, 3-phase machine is connected to a bus or maybe a transformer and then connected to a bus. There may be several lines that are then going on, may go somewhere, this may go somewhere, maybe another bus and so on. Now what is a very severe duty for the alternator? I mean, whenever you design a machine and you are going to design the switch gear to protect the machine and make it operate in a safe manner on the grid, one has to answer the question, what is the worst case situation that we are likely to encounter? And in that analysis what one does normally is to look at therefore fault performance of the machine. So if there is going to be a ground fault on the lines, what happens to the induction machine? So we are looking at what is then called as a 3-phase short circuit of the machine, and this test, 3-phase short circuit, sometimes called as sudden 3-phase short circuit, is a very important experiment that is done on the alternator to determine what will be its behavior when subjected to this kind of a disturbance. And there is a lot of analysis that has been done. Invariably in such cases, when there is a fault that occurs, the speed of the machine does not undergo a change immediately, because such alternators are invariably quite large, associated with a huge moment of inertia, and therefore when there is a fault at the stator, the entire system which is rotating at some speed, you do not expect it to suddenly change speed. So in this kind of an analysis what we are looking at is then to make use of the dynamic equations and predict what kind of flow of stator currents are likely to happen in the system when the speed is constant. Speed may be considered constant, and then there is a sudden 3-phase fault at the induction machine, that is a very severe duty. And it so turns out, in trying to analyze this behavior by means of analytical expressions, there are several important features of the alternator behavior that can be defined, which and several definitions emerge out of this analysis, which then go towards defining a particular machine. One then speaks of transient impedances, subtransient impedances that are associated with a particular machine. So far in the machine models that we have derived, we have not come across, or we have not defined any of these terms. All that we had for an alternator, for example, if it is a salient pole machine, we talk about the direct axis impedance and then the q axis impedance, whereas now in order to quantify the behavior of the alternator when connected to the grid and subject to disturbance, you will now have to come across different terms, new terms, which one designates as transient or subtransient impedances. Now these definitions and the behavior also has something intimately related to the behavior of damper bars, behavior of dampers inside the alternator. During the time, that is when subjected to a disturbance, these bars that are there will be in action for a short period of time until the speed becomes again close to synchronous speed, and after that the dampers are not active, but still because of the disturbance that is caused, some stator current disturbance and field current disturbances are likely to be there. So how do you identify what is the subtransient impedance, what is the transient impedance, why they arise? In order to understand all this, what we will now do is proceed by studying the 3-phase short circuit behavior of the alternator, starting from the dynamic equations of the machine, including the representation of dampers. So we will look at one damper circuit on D axis and one on the Q axis, make the equations for this, that is develop or by inspection the equation for this system, and from that equation we will then study how the machine responds to a sudden 3-phase short circuit. This we will see in the next class. We will stop here for now.